Okay, hello everyone. We're happy to have Professor Emily Riehl from Johns Hopkins University, and she's the thesis advisor of our David Jazz Myers here. Hi, Emily.
Hello.
And Emily is going to tell us about infinity category theory for undergraduates. Please, Emily.
Great. Thanks so much. Apologies again for the delay, but it's wonderful to see you now. I should start by explaining the title, which I think is a potential source of confusion, and I apologize, but it's kind of fun to use anyway. So this talk is not intended for an undergraduate audience, but I guess it's inspired by something that I really find astonishing, which is the amount of mathematics that we are able to teach to undergraduates, things that 100 years ago, 200 years ago, only a handful of people in the world understood at all are now boilerplate in the curriculum. And I'm interested in how that process happens and how my research area, which is infinite dimensional category theory, might eventually be absorbed into the canon in a way. Infinity categories don't interact yet with all areas of mathematics, and perhaps they never will. But in the experience in certain areas is that the objects that mathematicians study traditionally come with some sort of notion of transformation between them. And on occasion, higher dimensional transformations are needed. So there's this lovely metaphor for category theory due to Barry Mazur, which is as follows. So Mazur uses the metaphor that a category frames a template for a mathematical theory. So a category frames a template for a mathematical theory. I guess maybe we understood mathematics as the default context. I'll just write for a theory. And the point is that this theory should always have nouns. These are the objects in a category, and also verbs, the morphisms in the category. So objects traditionally written something like A, B, a morphism is depicted as an arrow between two objects. I mean, this is also a relatively novel point of view in terms of the history of mathematics. I mean, it was only around 100 years ago that mathematicians had this clear idea that a function should always come with a specified domain and a specified codomain, as opposed to just be encoded by some sort of expression. So a lot of modern mathematics develops using this categorical language. Most of the objects mathematicians study have some corresponding notion of transformation between them and fit into a category. But certain objects admit higher dimensional transformations, and that's really what infinity category theory is for. So now I should apologize to Barry Mazur by extending his analogy beyond all possible reason. But an infinity category, you might say, frames a template for a mathematical theory with nouns and verbs, and now adverbs, which are often thought about as two-dimensional morphisms. So the ordinary morphisms in a category might now be called one morphisms. And a picture of a two-dimensional morphism is something like this. It's a transformation between a parallel pair of one-dimensional morphisms. Now, the infinity refers to the fact that this process goes all the way up. So after the two-dimensional morphisms, there are three-dimensional morphisms between parallel two-dimensional morphisms, and so on and so forth. Sure.
To interrupt, can we ask you please not to write on the upper top right corner, because that's where your picture is.
I see. Okay.
So we can see nouns, verbs, adverbs, and
nothing to the right. Great. Okay, so yes, that's no problem. I can certainly accommodate that. And in any case, let's see. So here is what you missed. So great. Okay, so yeah, this is the one advantage of not being in person, I suppose. All right, so this is meant to give a very vague idea of what an infinity category is. So back to the title. I mean, the ultimate goal of this talk is to dream about how we might one day be able to teach this to undergraduates. And there's a big gap there because it's hard to teach infinity category theory to graduate students now, or even to experts. I mean, this is not an impossible problem, but the time resources demanded, I think, are larger than might be optimal. And I want to try and give a sense of why it is so hard to nail down a precise definition of an infinity category. One thing I can say about it is there's this analogy. So the relationship between an ordinary one-dimensional category with just the objects and the morphisms, and one of these infinity categories with infinite layers of morphisms is roughly that between an ordinary set and something called an infinity groupoid. So for experts, what I've conveyed in part by this analogy is that by infinity category today, I just mean infinity one category, which is sort of the base case of infinite dimensional category theory. You can ask me about higher dimensions later if you prefer. So this analogy, of course, is only useful if you have any idea what an infinity groupoid is. So I should explain that next. And I'll explain it by giving an example. In fact, I'll give the only example. So in a strong sense that I'll explain after I give the example. So these are the only examples of infinity groupoids. But let's actually warm up with something that I hope will be a little bit more familiar. So I want X to be a topological space. So I'll draw maybe this surface of genus 2, but you can imagine anything you want. It could have multiple components. In fact, it's interesting when it has multiple components. And in this setting, so this is the warm-up before the example of an infinity groupoid. I'm going to tell you about a category which is called the fundamental groupoid. The fundamental groupoid. This is very closely related to the fundamental group, if that's a more familiar concept. Notation is pi 1x. This is sort of a mini object version of the fundamental group. So this is firstly a category. So as Mazur teaches us, a category needs its nouns and its verbs. So we need objects and we need the morphisms. And the objects in this case are just the points inside the topological space. So here, here's a point A, a point B. These are two objects in the fundamental groupoid. And the morphisms are paths between points. So path is a continuous function from an interval into the space. There's a conventional orientation, so it has a starting point and a final point, except that's not quite right. These are really paths up to based homotopy. So what I've drawn in my picture is a path F, a particular continuous mapping, which starts at the point A and ends at the point B. If I had any other path, say this F prime, for which there exists a two-dimensional path, a path between paths, or homotopy, that is constant at the endpoints between them. So that's some continuous mapping from a disk that fills in the circle that I just constructed. Then these two paths will represent the same morphism in the fundamental groupoid. Whereas a path that went the other way around the hole, this path G, for instance, is not homotopic to the other two paths, and therefore represents a distinct morphism from A to B in the fundamental groupoid. Okay, so that's the basic, maybe the underlying directed graph structure of the fundamental groupoid. But it's also a category, which means in particular that paths can be composed. And there's something interesting about the categorical structure and the fundamental groupoid that I want to call your attention to. And it's the following. So if I consider three different paths, P, Q, and R, I'll draw them in just a second. So what I want to note is when the composite of paths P and Q is equal to R in the fundamental groupoid. So let me draw the picture. So suppose I have three different points down here. P is a path from X to Y. Q is a path from Y to Z. So because the end of P is Y and the start of Q is Y, these paths are composable. So there will exist a composite path. And there is, in this setting, there is a canonical way to define the composite. I can just sort of concatenate those two intervals. I could glue them together and then reparameterize, maybe to spend half of the time on the first interval and half of the time on the second interval. But the point is that's not the only, so the path that I've just described is not the only representation of the composite in the fundamental groupoid. Instead, because of this fact that the morphisms are really paths up to base homotopy, any other path R, like the one I'm drawing in now, for which there exists some homotopy filling in this triangle, and I should give this homotopy a name, so I'll call it alpha. So any other path R equipped with a homotopy alpha inhabiting that triangle defines a composite of P and Q in this fundamental groupoid. So that's an interesting perspective on composition that's here in the structure, that there's a sense, I mean, because the morphisms at the end of the day are equivalence classes, there's a sense in which composition is well defined, but the witnesses for this composition can be more interesting. So this is true if and only if there exists a homotopy alpha, as I've indicated in this picture. Okay, so the fundamental groupoid is a famous categorical invariant of topological spaces and homotopy types, but it's not a very rich one. So a problem with this invariant is that pi1 of Sn is contractible, is the singleton. The one is equivalent as a category to the terminal category for all n greater than or equal to 2. So this doesn't appreciate the difference between the higher dimensional spheres. These are sort of the atoms in homotopy theory, the fundamental homotopy types. So we'd much prefer an invariant that can tell them apart. And that's where the fundamental infinity groupoid comes in. So now I'm back to giving the only example of an infinity groupoid. The fundamental infinity groupoid. So this is denoted pi infinity at x. So the fundamental groupoid, one groupoid was a 1 category. This is an infinity category. So it has, again, objects in 1 morphisms. And we start out like the fundamental groupoid. So the objects are just the points in the topological space. The 1 morphisms now are a bit simpler. They're really just the paths, and we're no longer taking based homotopy classes of paths. So each individual path, like this F and this F prime, will represent distinct 1 morphisms in the fundamental infinity groupoid. Then we have, in addition, 2-dimensional morphisms, and these are these paths between paths, or the based homotopies I was referring to before. So paths between paths. But the reason I'm expressing them this way is now it's clear that these things can iterate. So we could have a path between a path between a path. That's a mapping from a 3-dimensional space into our space, paths between these, etc. And this continues all the way up. Okay, so there's a sense in which the fundamental infinity groupoid very naturally encodes the path algebra of the space, and that is just the data of all the points in the paths and then all of the higher paths. There's also a sense in which it's kind of a complete homotopy invariant of topological spaces. So this is expressed by something that's called Grothendieck's homotopy hypothesis. Homotopy hypothesis. And what it says is that the construction that I've just indicated, which takes a topological space, that was the X, and produces this fundamental infinity groupoid. So that's an example of an infinity groupoid. So this construction, well, there's various things that I can say. So firstly, if I take spaces up to homotopy equivalence, or maybe weak homotopy equivalence, depending on the point set topology subtleties, and infinity groupoids up to equivalence, then this is a bijection between equivalence classes of objects on one side and equivalence classes of objects on the other side. I can say something richer, though, which is that this is also an equivalence of infinity category. So that implies the fact on the bijection of equivalence classes on objects, but also indicates that there's some sort of higher structure that's respected by this correspondence. And in particular, on account of this equivalence, all infinity groupoids arise as fundamental infinity groupoids of some sort of topological space. Another perspective of this is that a synonym for infinity groupoid is the notion of homotopy type. So it's a space up to maybe weak homotopy equivalents. It's the data of a space that's captured by its set of path components, its fundamental group or fundamental groupoids, fundamental groups or fundamental groupoid, and then all the higher homotopy groups as well. But what I haven't really explained yet, so this is the sense in which the fundamental infinity groupoid is a good invariant of topological spaces. It completely distinguishes between homotopy types. But there's a challenge, as I haven't really explained yet how this structure is like a category. So I mentioned that this is an example of an infinity category, and so it has this sort of data of these paths, but the sort of central structure in a category is composition, and I haven't really discussed that at all. And a challenge, I guess, is we might say that the composition in this fundamental infinity groupoid is not well defined, or at least not well defined in the sense of ordinary things that are well defined, or sort of ordinary functions that are well defined. And I want to explore a little bit of that. I'm going to have to start scrolling though. So does anyone have any questions before we lose some of this text? Okay. Great. So what did I mean by saying that it's not well defined? Well, it's not well defined in the sense of this observation that we made above. So what we observed is that in the fundamental groupoid, which is a quotient of this fundamental infinity category, it's the homotopy category of this infinity category. So what we observed in the fundamental groupoid is that there are many paths R that represent the composite between a pair of paths P and Q. These paths are any path for which there exists this homotopy alpha filling in this triangle represents the composite. And there are many such paths. And there's a sense that when we're getting to the point of the fundamental infinity groupoid, there's no really canonical, there's no reason to prefer any one of these paths to any others. This has to do with associativity, for instance. If we wanted to make a particular choice of a binary composite, we should also have a particular choice of a ternary composite and a particular choice of a quaternary composite and so on. And those choices can't really be made compatibly. So a better perspective is not to make any choices at all and just accept the world as it comes to us, namely that there exist multiple composites of a given pair of paths. And so that's sort of what I meant by saying that this is not well defined. That's maybe a bit uncomfortable, but we have this theorem that sort of captures what remains good about this situation, which is that the space of composites of a composable pair of paths, so of say P and Q like above, in this fundamental infinity groupoid. So it's not a singleton, there's not a unique composite path anymore, but it is contractible. This is the form in which homotopical uniqueness conditions take, and this is a very prototypical statement. I like this one because it's not so hard to prove. So if you'll indulge me, I'll give a very quick proof of this. So firstly, what is this space of composites? So this is meant to be the moduli space. It's a topological space whose points are the data of a composite of paths P and Q. And what we saw above is that the data of a composite is really given by this pair of this path that is the composite path and this homotopy alpha that witnesses that composition relation. So if I write comp PQ for the space of composites, I'm going to realize it as a subspace of a mapping space from a solid two-dimensional triangle into the space X. So it's the data of a composite is in particular a continuous map from this triangle into X, but not an arbitrary continuous map. I only am interested in those maps so that when I restrict to the part of the triangle that looks like this little wedge shaped, formed by two of the boundary paths. When I restrict, I get a particular continuous map, namely the one given by the paths P and Q. So the paths P and Q together define a point in this bottom mapping space. And I want to consider continuous maps from the triangle that are extensions of that particular map. In other words, I can define this space of composites to be the fiber of this map, or just the sort of the inverse image. It's a particular subspace. All right, so my goal is to show that this space is contractible. And one way to do that is to consider an arbitrary sphere mapping into here, and then the challenge of extending that sphere to a disk. So this should be for all n greater than or equal to 0. So because this space was defined by a pullback, it's equally the challenge of constructing this second dashed map in lighter green that makes the whole picture that I've just drawn commute. So it has to restrict along this inclusion to the top specified map from the sphere, and it also has to respect this bottom commutative triangle. Now, it's maybe not so clear that this problem has a solution, but we can re-express it a different way. So categorically, I'd say I'm transposing across a 2-variable junction. So my goal again is to construct a continuous map from the disk into the mapping space, or in other words, from this disk across this triangle into X. So that's my goal. And I'm given some constraints as specified by the solid arrows in this diagram. So in particular, I have a specific map already from the sphere across the triangle into X, and also from the disk across this wedge-shaped portion of the triangle into X. That's given by the top and bottom components of this rectangle. And then these glue together along this common subspace that has to do with the commutativity of this rectangle. And so now this is my new goal. And this problem can be more easily solved. So in the case where n is equal to 1, this bottom shape is a triangular prism, which I like to think of as some sort of pig's trough. And the top shape is the part of the pig's trough that would be made of wood and not of pig food. So that's the sides and the triangular sides, and then the bottom two rectangular pieces. And you can imagine if pigs are eating their food in their trough, then the level will sort of continuously go down. This is defining a continuous deformation or tract. So there's a continuous map from here back to here. So my desired lift just composes this way and then goes across. Okay, so that's a quick proof that this space is contractible. Okay, so essentially, I mean, what this example illustrates is really this analogy that I mentioned above, connecting categories and infinity categories. I can say something a little deeper about it. So if I stated the definition of a category, which I haven't done, I apologize, I would state it in the language of set theory. So a category, or a small category, has a set of objects, and between any two objects, a set of morphisms. And then there are these various axioms that are expressed in the language of set theory. For instance, the existence of a composition function relating these Hom sets that satisfy certain properties expressed in terms of an equality. If I wanted to state the definition of an infinity category, what I would have to do now is replace firstly all of the sets by an infinity groupoids. So an infinity category has an infinity groupoid of objects. It also has between any two objects an infinity groupoid of morphisms. But I also need to replace the further axioms by the corresponding notions in the language of infinity groupoids. So instead of having a composition function, I would have a map of infinity groupoids playing the role of composition. But maps between infinity groupoids are a little bit confusing. An infinity groupoid, remember, by the homotopy hypothesis, is like a homotopy type. So it doesn't have an underlying set of points. It has a set of path components, but not really a set of points. So these maps between infinity groupoids aren't really functions in the way that we are usually familiar with. There's a sense in which anything ever is only well-defined up to a contractible space of choices, like we saw in this theorem about the homotopical uniqueness of composition in the fundamental infinity groupoid. And so now I'm pretty far removed from the sort of Bourbachian language that mathematicians use to make their rigorous definitions. And this is a real problem. So there's ways that we get around it, that people who work in the field of infinity category theory are able to give precise definitions of an infinity category in the language of set theory. This involves something called models of infinity categories that go by various names you might have heard of: quasi-categories, complete Siegel spaces, Siegel categories, and so on. This is something that's very interesting to me, and I've spent a lot of work working with these models. But I think it's entirely unsuitable for the ultimate dream of this talk, which is eventually to teach this material to undergraduates. And I mean, essentially just because it's sort of too technical and it takes too much time. So here's kind of the new idea, and this will transition to the second part of the talk. But the new idea is that, I mean, again, I'm really trying to answer this question, you know, how will we ever teach? How will we ever be able to, if we want to, how will we ever teach this to undergraduates? And what I'd like to explore is a possible answer, which is to ask our foundation system to do a bit more of the work, ask the foundations to do more work. So now we're transitioning to the more speculative part of the talk, though there will be some theorems here as well that I will mention. So I have a specific foundation system in mind that, you know, conjecturally would provide a much more convenient language within which to develop infinity category theory than the traditional foundations in set theory. So this foundation system is still very much under development by people like David Jazz, who you know very well. And you know what it would look like in 100 years could be quite different from today, but it's sort of fun to get a little bit out over our skis and think ahead right now. So this foundation system goes by the name of dependent type theory, which was intended as just an alternative approach to set theoretic foundation. So type theory goes back to Russell, the form of dependent type theory that I'll discuss. It was developed by Martin Löf in the 70s. But this is supplemented by something called the univalence axiom due to Vladimir Voevodsky, which introduces, among other things, a new perspective on this dependent type theory foundation system. It allows us to think, it allows us to give a homotopical perspective or a homotopical approach on this dependent type theory. And so I'd like to tell you a bit about that next, but I'll stop again and see if there are any questions first.
All good, Emily. All good, you can.
Okay, cool, let's give it a go. So you might have some exposure to dependent type theory, but let me give you a quick kind of crash course review. So my dream is that, actually, I kind of think that undergraduates today should be learning dependent type theory, maybe not super formally, like the way that you would teach a computer dependent type theory by listing out all of the rules in total rigor, but informally, like the way that we traditionally teach undergraduates set theory. So, I mean, of course, that process takes a bit more time than we have today, but I'm going to try and give you a glimpse. Sorry, my computer's doing something weird. In just a few minutes. So there are following primitive notions in dependent type theory. So in set theory, we don't ever really define what a set is. We just learn to get used to sets by learning about their structure. It's similar in dependent type theory. So that we have the following primitive notions. So firstly, there are things called types. So examples include the type of natural numbers, the type of real numbers, also things like the type of groups. So each type then also has some terms. So terms in these types include 17 is a natural number, square root of 2 is a real number, the Klein 4 group is a group. So each term belongs to a unique type. You could map a term from one type to another type if you want a notion of 17 in the real numbers. Of course, that's where, but the terms are sort of well typed. And then what makes type theory, dependent type theory, is that we also have as a primitive a notion of a type family, a family of types. And so what this means is that a type can depend on a term in another type, or a sort of variable in another type. So for instance, we have n-dimensional Euclidean space. That's a notion that mathematicians are very familiar with. But to talk about n-dimensional Euclidean space, we first need an n. And what this n is, it's a natural number, a term of type n. So similarly, we could think about for n and n, the type of fields of characteristic n. So what's interesting about this example is, of course, for certain n, there will be no fields of characteristic n. This only makes sense if n is a prime number, but that's okay. We still have this type family. It's just some of these types are empty. So when n is not prime, it will be impossible to construct a term in this type, because it's impossible to construct a field of characteristic 4, for instance. We can also have type families that depend on multiple terms. So if I had a group G and a field K, maybe I don't care about its characteristic anymore. I can think about the type of representations of G over the field K. So representations as K vector spaces, for instance. So those are the type families. And then I also have term families. So term families, for instance, so in my first type family, I have this family of terms, which are the 0 vectors in Euclidean space for each n. I do not have any term families in this second type, the fields of characteristic n, because again, I cannot construct a field of characteristic 4 or characteristic 6 and so on. But I could, if I considered a similar family of, say, rings of characteristic n as opposed to fields of characteristic n, then I do again have a term family. So for each n, I can construct the cyclic, the field z mod n. Sorry, the ring, it's not a field, the ring z mod n, which is a ring of characteristic n. So that works well. Or in this final family where for an arbitrary group G and an arbitrary field K, I can construct its regular representation. That's an example of a representation of G over K, for instance. So these are the notions of term families. They can be thought of as functions that take in an arbitrary pair of variables, sequence of variables, and produce a term in the type that depends on these variables. So great. So there's certain operations that I can do on these primitive notions, on these type families and term families. So if I'm given an arbitrary type family, and here I'm using some sort of homotopical notation. I'm already gesturing at this homotopical interpretation. So it's traditional to use E and B to think of fibration in topology. B is the base space, and E's given a point, a little b, and the base space E of B would be the fiber of the fibration over B. So that's an intuition for these type families. So given something like this, I can form. So on the one hand, I can form something called the dependent sum type. The notation is really borrowed from set theory. So I could also think of a type family like an index family of sets. And if I had an index family of sets, I could form the sum over the indexing set of all of the sets in the family, or this sort of index sum. This is I guess a disjoint sum. In fibration world, this is the sort of total space where I've just sort of glued together all of the fibers. So for instance, the type of fields can be assembled as the sum of the type family of fields of characteristic n, field characteristic n, for instance. So a term in this type is an index. So in this case, it would be a prime number like 7, and then a field of characteristic 7, or I guess 0, of course, with fields of characteristic 0 as well. And then I can also form another construction called the dependent function type. Dependent function type. And the notation for this, it looks like a product of an index family, and that's a way to think about it. A term in here Also, so an example, this type exists for any type family. So for instance, I can think about my rings or fields of characteristic n and form this dependent function type, but only in the case of rings will this have any terms, which is why I prefer that. And a term can be thought of as a function that takes an input, so a natural number n, and then produces a ring of that characteristic. So this is usually written in different notation, but this is the function that takes an n and maps it to this ring of characteristic n. Okay, so what really animates Martin Luf's dependent type theory is something called identity types. Identity types, and I'll want to briefly introduce them and their rules. So identity types satisfy the following rules. So the first one is just that for any type A and any pair of terms in that type, there is a type family here. So this, in a sense, is kind of the most confusing rule. I think of it as like a no nonsense rule. And so one role played by types in dependent type theory is they're used to sort of state, grammatically correct mathematical assertions, which may then be true or false. So what you should read this x equals y as saying is that it's, so firstly, this is the name of a type. X equals AY is the name of a type, just like group was the name of a type, or natural numbers is the name of a type. This is a type that depends on having already two terms of type A. And this type is asserting that it's meaningful to inquire whether X and Y might be identified as long as they are two terms of the same type. So it's not meaningful to try and identify terms of different types. It wouldn't make sense to ask whether your group is equal to the square root of 2. I mean, that's not a well-typed question. But if you have a group, the Klein 4 group, and a group, the cyclic group of order 4, it is meaningful to ask whether those can be identified as groups. In that case, that's false because those are distinct groups, but it's a meaningful question to ask. It would be a reasonable question to ask whether two different groups can be identified. Okay, so just because we have a type that's a place where proofs of equality could live doesn't necessarily mean that we have any proofs of equality. So what the second rule says is that the type x equals x is always inhabited. So in other words, it's always true that x can be identified with itself. And we call the proof reflexivity. So the proof here is given by a term. There's a term, reflexivity, that witnesses the truth of the fact that x is equal to x. Okay, so the third rule I'm going to call indiscernibility of identicals. This is after Leibniz's indiscernibility of identicals, which I'll comment more about in just a second. This is not really a fair name for this rule because it doesn't quite reflect its full power. The way I'm going to say it very informally is that the identity type family is freely generated by the reflexivity terms. Type family is freely generated by reflexivity terms. Generated by the reflexivity terms. So, so given more time, I would explain that there's a very close analogy between the identity type family and the type of natural numbers. Both of these types can be described inductively, that all their terms are sort of freely generated by some base cases. In the case of the natural numbers, it's the term 0 and then this successor function that takes a natural number n and produces its successor. In the identity type family, it's these reflexivity terms. They somehow freely generate the whole family in this sense. And one of the axioms that characterizes the natural numbers, both in traditional foundations and also in dependent type theory, is this principle of mathematical induction, which can be understood as the assertion that the natural numbers are freely generated by 0 and successor. And there's an analogous principle here that implies, in particular, Leibniz's indiscernibility of identicals. So what that states is that once you have a proof that x is equal to y, then any properties of x must also be true of Y and conversely. And that can be understood as a consequence of, as a consequence of this. Let me just mention this as a corollary. So if I'm given an arbitrary type family and a term in some identity type in the base, so a proof P that X can be identified with Y, so X and Y are then terms in this base type B, then I have a function which is traditionally called transport along P that goes from the fiber over X to the fiber over Y. So this is in topology, this is the operation of path lifting. If I have a path on the base of a vibration, then there's an associated function between the fibers, a continuous function between the fibers. In topology, that function is an equivalence, and the same is true here, though I haven't yet defined equivalence between types for you. This is not the full strength of this third axiom about the identity type family, but it is a consequence of this, and this is sort of most closely analogous to Leibniz's indiscernibility of identicals. So, so the point of these new foundations is they were supposed to have something to do with homotopy types as primitives or infinity groupoids as primitives, and I'll draw a picture illustrating this. So I might call this the world according to homotopy type theory. So this homotopical perspective on dependent type theory, according to, there's a standard acronym used for that, HOTT, homotopy type theory. So I mentioned we have these primitive notions of types, and I'm going to draw kind of a big box for my primitive notions of types. This perspective is due to Vladimir Voivodsky. And among the types, I have certain types which are called sets. Sets are also known as the zero-dimensional types, and these include things like the natural numbers and R are both understood as sets. There's a layer below the type of sets, which are called propositions or -1 types. And these are the types that are sort of essentially just truth values. So there's an empty type, which has no terms, and a type that sort of freely has one term, a singleton type. There's a level below this as well, which are the contractible types. So contractible means in particular that you're inhabited. So there's always a point in the contractible types. These are the -2 types, and they include this point. But we have higher levels as well. So we have 1 types. And so what is this hierarchy? This hierarchy has to do with how complicated an identity, the identity types are. So let me tell you about the 1 types, and then I'll give you that definition. So the 1 types include things like the circle, which is a homotopy 1 type, also the torus, another homotopy 1 type, RP infinity, but also things like this type of groups. So what characterizes the 1 types is the following. We say that B is an N type if for all pairs of terms, X, Y, and B, the identity type between those terms is an N-1 type. So this gives a definition of all of the levels in this hierarchy except for the base one, which I'm going to leave to your imagination. So above the 1 types, we have the 2 types. So 1 type is type so that its identity types are sets. A set is a type whose identity types are propositions. Proposition is a type whose identity types are contractible. So 2 types include things like homotopy 2 types, CP infinity. And then there's also types that are untruncated. So the higher dimensional spheres live all the way up here, for instance. Maybe the universe of all types lives up here. So a perspective on homotopy type theory is that traditional foundations appear here. So traditional foundations concern set theory and logic, so the sets and the propositions. And while it's not quite natural to assume sort of classical reasoning principles like the axiom of choice and the law of excluded middle, it is consistent to assume them, provided you restrict them to this level. So the axiom of choice is about inhabiting a product of a non-empty family of sets, or a family of non-empty sets. And the law of excluded middle is about deciding P or not P when P is a proposition. So it's okay to add those principles, but This perspective on mathematical foundations is that some mathematical notions exist at that level. We have a logic level, we have a set level, but then there are other mathematical structures that are really richer, that have a more complicated notion of identification, and those come in at these higher levels as well. Okay, so what really ties this whole theory together is Voevodsky's univalence axiom. And maybe in the interest of time, since I'm running a little late, let me just say that univalence characterizes the identity types, characterizes identifications between types themselves, identifications between types as equivalences, and has a whole bunch of wonderful consequences that I'm sure David would be very happy to tell you about if he hasn't already. But in the last, I was told I could take back the time that I lost. So in the last few minutes, I'd like to wrap up by bringing us back to infinity category theory and explore that within these new foundations. But I'll pause for a second and see if there are any questions before wrapping us up.
So, hello. So in the corollary, I think it's the only arrow that you write in this page is on the transport map. I mean, what does it mean?
Yes, sure. Thanks for that question. So this EX firstly is the name of a type. It's one of the types that belongs to this family of types that I assumed I was given. EY is then also a name of a type. This is when I substitute X and Y for the B in that type family. And then this EX2EY is actually also the name of a type. This is the notation typically used for the function type. So one of the basic constructions in type theory is this operation that takes any pair of types and produces its function type. And what this transport then is it's a term as expressed by this colon in this type of functions. So informally, it's a function that would take a term in this type and produce a term in this type using the information of this path P, this identification between X and Y. So I certainly did not explain that very well. Thank you for that question. Okay, great. So let me try and bring this back to infinity category theory. So first I've introduced a new foundation system, and that's a little bit scary. So I should comment briefly on what this has to do with traditional foundations. So what's referred to as homotopy type theory or / univalent foundations is dependent type theory plus the univalence axiom, which I didn't really state for you, but this is a new ingredient in dependent type theory. And Voevodsky both stated the axiom and proved its relative consistency by constructing a model of this formal system in topological spaces, but maybe I'll describe it as the infinity topos of spaces. So in this model, types are associated with spaces, type families are associated with vibrations, and so on and so forth. The reason that I mentioned that this lands in the infinity topos of spaces is that Mike Schulman recently extended this theorem and showed that homotopy type theory with the univalence axiom has semantics in any infinity topos. So this is sheaves on, these are sort of higher dimensional sheaves on a sort of higher dimensional site. So it's a sort of infinity groupoid analog of the traditional notion of a one topos. This is a realm for synthetic homotopy theory, if you will. And so what these results mean is that any theorems that are proven in this formal language, in this formal system of homotopy type theory are true, have semantics in, have implications for both traditional homotopy theory and also other homotopy theories, parametrized homotopy theory, equivariant homotopy theory, and so on and so forth. So what I'm about to tell you about now is something that I'll call simplicial homotopy type theory. So this is an extension of homotopy type theory in a sense that I'm about to explain. And by results of mine with Mike Schulman, and also results of Jonathan Weinberger, who is a recent PhD graduate, now a postdoc with me. This has semantics in one of the models of infinity categories. So this is the model called complete Siegel spaces due to Charles Resk. So this is a well understood, well kind of loved model of infinity category theory. What this means is that the mathematics that I'm about to describe in this new unfamiliar formal system is real mathematics. So via this interpretation, this is a strategy for proving theorems about complete Siegel spaces, and via that theorems about infinity categories in arbitrary models. Okay, so what on earth is this simplicial type theory? So in simplicial homotopy type theory, in simplicial hot, so we still have our type families as before, but type families might depend on polytopes in directed cubes, and so in a way that is detailed in our paper. But the main implication of this for us is that if I'm given an inclusion of polytopes, so by a polytope, you might think of something like a simplex or a subcomplex of a simplex. So this is an inclusion of polytopes. And a function that maps from a polytope into a type A. There is a type whose notation I'm going to introduce in sort of a cartoonish way to help us figure out how to think about it. So it's a type of extensions of my specified function to a function from the larger polytope. So it's a type of extensions of f to a function on the larger polytope psi. So a term in this type is a function from psi into A that restricts along phi to the specified function f. Okay, so that is a very, very brief overview, but the upshot, the thing that we actually care about, is in this formal system, each type A has two different type families. So has firstly its identity type family. So this is one we've seen before. So for any pair of terms of type A, I have the type whose terms I might think of as paths or identifications between them. This captures the infinity groupoid structure of the type A. But then I also have a second type family, which I'll denote this way, Hom AXY. And this is a type, we might say, of paths in A, where this is a type of arrows. So if I'm about to talk about category theory, or really infinity category theory, I need access to the directed arrows inside a type, and that's provided by this simplicial type theory formalism. So, and I mean, another way to think about this is if you're familiar at all with complete Siegel spaces, they have both a sort of categorical direction and a homotopical direction, and that's what's encoded by these two different type families. Okay, so what can we do in this formal system? So admittedly, I haven't explained the foundations very well, but I can explain their consequences, and I think that might be more interesting in any case. So a thing that we're unable to do easily in traditional foundations, but we can do here, is actually give a definition of an infinity category. So this whole talk was meant to be on infinity categories, and I have completely neglected to define infinity categories, so that I can do that now. So in this new foundation system, I can define an infinity category as follows. So an infinity category is a type in which two things are true. So firstly, each composable pair of arrows has a unique composite. Of arrows has a unique composite. Okay, so this, I mean, firstly, this is what's true in ordinary category theory. For one category, so it's certainly the case that a composable pair of arrows has a unique composite that's specified as part of the one category structure. This seems strange because it's kind of completely false in infinity categories. What we learned above in the sort of example of an infinity category that we considered is that it's not the case that we have a unique composite. Instead, we have a contractible space of composites. But this is one of the main points of this formal system. In this sort of homotopy world, contractability is indistinguishable from uniqueness. So to an undergraduate who has learned this as their foundation system, uniqueness for them will mean contractability. If I have a type that is contractible in this sort of hierarchy of types, it's sort of indistinguishable from a type that only has one term. But semantically, when I interpret it in sort of traditional mathematics, this really does reflect contractible moduli spaces. So that's one of the things that's so wonderful about this formal system. So again, exactly what I mean by this easy to understand statement, a composable pair of arrows as a unique composite, is that if I look at this shape, so a composable pair of arrows would define a continuous map from here into A. And then I could consider an extension to the 2 simplex or to this triangle. This type is contractible. And that's exactly what we proved semantically above. That's what's been asserted axiomatically here as one of the characteristic properties of an infinity category. So there's a second axiom as well, which, if you know about the difference between a Siegel space and a complete Siegel space, is the thing that you would expect. It's that identifications are equivalent to isomorphisms, are equivalent to isomorphism. So this is some connection between the sort of path structure as encoded by this identity type family and the categorical structure as encoded by this type family. Okay, so one of the takeaways in this new foundation system is that you can actually give a definition of an infinity category, which is, something that's a lot more difficult than traditional foundations. The definitions that we do have given in models are somehow beside the point. They introduce these coordinates that are not really fundamental part of the theory, and it's like having to choose a basis every time you want to do anything, even though you feel like there should be a basis-free construction. But sort of where this theory really shines is when we start to prove theorems. So one of the fundamental theorems of ordinary category theory, equally infinity category theory, is the innate lemma. And it's quite complicated to both state and prove the innate lemma in infinity category theory. But in this formalism, I can give a statement and a proof that is as simple as the classical one, which is a really magical thing. Let me not state the fully general innate lemma. I'm going to state just a special case. But let A be an infinity category, and let X and Y be terms of type A. You'll say A and B. Let A and B be terms of type A. Then the type of arrows between A and B is equivalent to, so it should be the type of natural transformations between the corresponding represented functors. So the represented functor, the functor contravariantly represented by A is this one. The family of types contravariantly represented by B is this one. And here I'm going to take one of these dependent function types. So what I'm asserting here in this innate lemma is an equivalence between this type on the left and this type on the right. So a term in this type is a function that would take in an X and then an arrow from X to Y, or sorry, from X to A, and then return an arrow from X to B. There's nothing in this construction that asserts, so this is like the components of a natural transformation between represented functors. There's nothing in this type family that asserts the naturality here. And in fact, naturality is for free. So this is the sense in which this is in fact simpler than the traditional innate lemma. So because I have only a tiny bit of space, I won't write any more about the proof, but let me just say a little bit orally. So if you were to prove the traditional innate lemma, what you would do is you would just construct an explicit equivalence between these two types. So you would construct a function that would take an arrow from A to B and then induce a natural transformation. And then you could construct a function that takes a natural transformation and recovers an arrow. So the construction in the direction from right to left is quite simple. So if I had a natural transformation, I would just evaluate it at the identity arrow at the term A, and that would recover an arrow here. So that's simple to write down even in traditional foundations. What's not so simple in traditional foundations is the function that goes in the other direction. But here, said I wasn't going to write, but I can't resist. The construction in this other direction would take an arrow from A to B, take a term of type A, take an arrow from X to A, and then simply return the composite arrow. Now I have to get composition in the right order. So that's F composed G. So this is a well-defined construction by this axiom that we have unique composites, unique up to homotopy. And this mapping on terms really does suffice to describe the inverse equivalence to the evaluation function. And then the proof that those two maps are equivalences is the same as the usual one. Okay, I'll stop there. Thanks so much for your attention, and apologies again for being a little bit late. No.
Thank you. Any further questions for Emily?
Hi, Emily. Can you hear me if I speak like this? Fine. Can you hear me?
Yes, I can. Thanks.
So I'm actually wondering, did you actually try this on undergraduates?
Right. So, I mean, the challenge is I need undergraduates who know dependent type theory and know homotopy type theory. So those undergraduates don't exist today. But I would love to try it with undergraduates who knew homotopy type theory. I mean, what I would envision is, over the course of a semester to an advanced undergraduate, who might be prepared to learn, a little bit of representation theory or a little bit of, algebraic number theory, or, some of the topics that exist at the advanced undergraduate level on occasion. So to that sort of student who already knew homotopy type theory, I think I could teach at least some basic infinity category theory in a way that would not feel quite so different from basic one category theory, because the sort of distance between an infinity category and a one category is really collapsed in this formal system, because infinity groupoids now aren't so different from sets. So that's a bit of an exaggeration, because the amount of infinity category theory that's been developed in this framework is considerably less than the amount of infinity category theory that exists at the expert level, or even one category theory that exists at the undergraduate level. So we don't yet have a theory of monads, for instance, but but some undergraduate courses in category theory don't discuss monads, so maybe it's okay. I could certainly do Yaneda lemma, adjunctions, limits, and colimits. Oh.
Yes.
Yeah, apparently now some forms of category theory are being taught at the elementary school level.
I don't know that I would advocate for that, but so
Elementary things, of course. Any other questions? Comments?
Hi, Emily.
hey,
You know this person?
Hi, nice
Yeah.
to see you.
hey, good to see you.
In going from infinity groupoids to infinity categories, you had to sort of change the type here. Do you, when you think about how this will go for, how like this kind of mathematics will be brought into sort of the mainstream, and in the future where we're teaching this to undergrads, advanced undergrads perhaps, do you see this process of going from one type theory to another to be part of that? And
Yeah, I think that's right. So I'm not really an expert in type theory as much as David is, but some of the philosophy that I've absorbed from colleagues is that there's less of a desire for one unified foundation, as mathematicians might expect. So there's lots of different flavors of type theory where the rules are changed a little bit, the nature of the contexts are changed a little bit to capture particular structures that are present in particular mathematical contexts. So this is maybe not so unfamiliar to a category theorist either, who's used to working with different sorts of structured categories. Sometimes they're Cartesian closed, sometimes they're locally Cartesian closed, sometimes they're topoi, sometimes they're topoi without choice or something like this. So I think of this as being something kind of analogous to that. I'll admit it's not entirely so clear to me how we would teach undergraduates this level of flexibility to, you know, sort of work with a different type theory in every course that they're taking in their curriculum. But I don't know, I guess that seems like a solvable expository problem. So yeah, certainly in an undergraduate course, I would have spent a lot more time explaining what simplicial homotopy type theory actually means. So those are rules that you can write down and be more explicit about. But yeah, I don't know. What do you think? So,
What do you think?
But I think, yeah, I think that I think this is actually one of the sort of big problems that to solve in type theory is how do we make this process, like currently it's quite ad hoc, right? You have to come up with this type theory to do category theory, and you know, you have to come up with another type theory to do differential geometry, and you have to come up with another type theory to do, you know, synthetic spectra and stable homotopy theory. And you know, it'd be great to have sort of a sort of, I guess, another meta layer where you can say, okay, in this class, here's the things we're taking for granted, and that would present the type theory, and that would be something like that. But I think I'm hopeful about it. I'm trying to work with Mitchell here on something like this. So
That's Mitchell.
oh, I can't wait to hear more about it. So, hey, so. Yeah, and I should admit, I mean, this is not, so, you know, Mitchell might know this even better than I do. This simplicial homotopy type theory that I was gesturing at here is probably not the correct type theory to develop a full theory of infinity categories. We need maybe some sort of cubical ingredients so we can reason about the universes internally to the theory, and that doesn't seem to be possible in the sort of initial formalism. But really this program is sort of work in progress that I expect to be completed in about 100 years. So I think we have some time to get those out.
Shouldn't hold up there. Yeah, this is very exciting. Any other question or comment? Okay, great. Thank you so much, Emily, again, for the very nice time.
Great.